We will start the session. The title of the session is Basics of System and Equipment Earthing. Now, we will start with the understanding what is earthing. Now, this is like a fundamental question. Yes, when you say earthing, the best method of learning is asking what, why, what and why, where and when, all those questions you put. I normally start, what is earthing? There are very many definitions. As many participants are there, as many people are there, as many definitions could be there. But I like to quote from the standard. The standard says by earthing, we mean making a physical and electrical connection to the general mass of earth. The general mass of earth means the earth on which we stand. The connection has to be physical. It cannot be imaginary. At the same time, if you make a connection with a non-conductive part, it is no earthing. So it has to be electrically conductive connection. That is what the standard mentions. So this is the understanding of what we mean by earthing. By earthing, we mean making a physical and electrical connection to the general mass of earth. Then the $1,000,000 question, I call it a $1,000,000 question. Then there is always this question, what is the difference between earthing and grounding? I have seen enough number of arguments, enough number of fights, going on and off the net in my classes, in my training sessions, in my whenever when I discussed on my projects with my clients, consultants. There are very many different of opinions. Somebody say they are the same, somebody say they are different. Let us see in spite of everybody's opinion, standards is the Bible. Standards are the Bible. Let us also see what the opinions of the experts and what the opinion, what does the standard says on this. Now, many people, including the so-called experts, now I would call, even many people have written tons and tons of books on earthing, and they also have felt to opine differently, argue that they have said that earthing is different and grounding is different. They have made this particular explanation. Grounding is connection of current carrying parts to ground. That is again neutral. Whenever they say if you connect the neutral to the earth, they say that that should be called grounding, and it is for equipment safety and safety of the system. And the earthing means non-current carrying, like the body of the panel board, body of the switchboard enclosure, or motor enclosure, or light fitting enclosure, whatever metal enclosures you are connecting to earth, they consider that to be earthing. And they say that earthing is for human safety. They clearly, these people who feel that earthing and grounding are different, they give this explanation. Grounding is system earthing, and earthing is equipment earthing. This is what they say. But I don't go by them. Then yes, I agree. I have heard and learned, read all these explanations, and then I wanted to find whether it is true what is said in the standard. After all, whenever any specification is given to us, any technical specification is given to us to follow, to design a system or to implement a system or to operate and maintain a system, we have to follow some national or international standards. So I just referred to very many standards and very many application guides published by government agencies, government approved regulatory authorities. So I found some strange conclusions. Now, the first Bible, as far as India is concerned, uh, the first Bible is IS 3043, that is code Indian Standard Code of Practice for Earthing. In the very first chapter, in the very first introduction itself, this code very precisely and very unambiguously mentions that in this code, that is in this code of Indian Standard Code of Practice for Earthing, the terms earthing and grounding are used synonymously. Synonymously means they have the same meaning. There is no difference whatsoever between earthing and meaning as far as Indian standard on earthing is concerned. That means earthing and grounding are the same, imply the same meaning. There is no difference whatsoever between earthing and grounding. This is a quote from the Indian standard. This is not my opinion per se. It is what is said in the Indian Standard Code of Practice for Earthing. Then I referred to the international terminology. Okay, at least the Indians, let us forget Indians. What is the other Bible, bigger Bible says? IEC, Electrotechnical Vocabulary 60050. It has a particular section on earthing, electrotechnical vocabulary for earthing. They very clearly say Wherever they have put the term earth, they immediately they put an oblique, and they have mentioned ground also. Earth or ground, earthing or grounding. In every definition, they have used both these words. In every class of this standard, wherever the term earth or earthing is explained, the title subtitle also mentions ground or grounding with a bracket US. So even in an IEC standard, the terms earth and ground, earthing and grounding are used synonymously only. And again, if you see the definition of the terminology of earth or earthing in the electrotechnical vocabulary, that is class 1950108 of the IEC 60050 subsection, you say to earth or to ground, both these terms are appearing in the standard. To earth or to ground is explained to make an electric connection between a given point in the system or installation or in an equipment to the local earth. That they also clearly specify that the earth or ground is one and the same, even in IEC. So it is clear from the term, even in IEC, earthing and grounding are same. There is no difference. Then there is another publication. Okay, leave alone the standards. People, some of the participants are most of the participants are aware of a good publication called Earthing Practice. This is published by Copper Development Association. They have publication number 119. They also say that in chapter 1, before discussing definition, it is worth noting that in Europe, because this Copper Development Association is headquartered in Europe, so they say in Europe, we follow the term, we use the term earthing, while in North America, the term grounding is more common. That means again, earthing and grounding are same. The IEEE definition, the same book, the Copper Development Association book further elaborates. The IEEE definition of grounding is ground or ground system, a conducting connection, whether intentional or accidental, by which an electric circuit or equipment is connected to the earth. Then, if you see the for use within Europe, if the generally you in the previous IEEE definition, you use find and replace. Find ground and replace with earth. The definition is IEC definition automatically fits in. So earth or earth system, in IEEE definition it was ground or ground system. In IEEE, if you in the IEEE definition, if you replace ground with earth, the paragraph is same. The definition is same. A conducting connection, whatever appears in verbatim appears in IEEE is verbatim reproduced in IEC, except the term earth in place of ground. Then there is a very popular publication in India, CBIP, Central Board of Irrigation and Power. They have brought out a publication, manual on earthing of AC power systems. The publication number 339. In that, it is clearly mentioned the term earth in US it is referred to as ground. That otherwise the meaning is same, except for the geographical difference, the meaning is same. Here too, even in couple of much acclaimed publications like CDA publication, like CBIP publication, it is acknowledged that the terms earthing and grounding mean and imply the same, and that there is no difference between the terms earthing and grounding. I happen to, I was saying that I happen to participate in various technical forums asking Q&A sessions. I used to ask my doubts as questions, and I used to answer questions in the forums as much as possible to my knowledge goes. So one time a person beautifully asked the same question was asked in the forum also. One forum is there called CR4. In CR4 forum some years back, when somebody has asked this question, what is the difference between grounding and earthing? I like one answer. There are many answers like mine. Many people have given very logical answers. Then one person has given a very beautiful answer, two-word, very short and brief answer. He has answered the difference between grounding and earthing is the Atlantic Ocean. You got the point. The Atlantic Ocean separates the continents US and Europe. So in one part of the Atlantic Ocean, in western part of the Atlantic Ocean, US, ground is used. In the eastern part of the Atlantic Ocean, in Europe, earth is used. He beautifully said the difference between earth and ground is the Atlantic Ocean. So that is what I have mentioned here. When this question, what is the difference between earth and ground, was posted in a professional forum some years back, someone had beautifully quipped that the difference is the Atlantic Ocean. That means the Atlantic Ocean separates the continents America and Europe. At the American side of the Atlantic, they use the term grounding, and at the European side, they are using earthing. Otherwise, there is no difference whatsoever between the terms and earthing and grounding. You may go on arguing with me, you may go on countering me, but this is what the standards say. And I am a stickler to the standards. I will not bother about any expert's opinion. I will go by the standards. If you can argue that there is a difference between earthing and grounding, quoting some national or international standard, let us see. So to conclude, irrespective of what some experts feel and opine about any difference between earthing and grounding, there is not any difference whatsoever between these two terminologies as per national and international standards. We have seen IS, we have seen IEC, we have seen IEEE. In all these three standards, they have not perceived any difference between earthing and grounding. So it is better to follow the standards rather than these expert opinion, because in any specification, design, installation, O&M specifications, customer, client, consultants, they only mention us to follow standards in our practices, design practice or installation practice or O&M practice. We have to follow only the national standard or international standard. So whenever you see a specification, perhaps if you are in India, they will say you have to go by IS 3043, not so-and-so's book, not so-and-so's book on earthing, not so-and-so's textbook on earthing. So you are asked to follow certain standards only. And as we could see, there is no difference mentioned in the standards between the terms grounding and earthing. So with that controversial discussion, we will move forward. So when we come to types of earthing, there are four types of earthing that we practice in any installation, industrial or okay, whatever, commercial, industrial or domestic, whatever it is, to the extent possible. We have heard of system earthing, equipment earthing, lightning protection earthing, and static earthing. Now, these are the broad classifications. So in this session, as we are going to discuss system and equipment earthing only, which is related to electrical installations, and lightning protection earthing is again a vast subject by itself. That is again protecting the buildings and structures against the harmful effects of lightning strokes. That has got a very big standard by itself, 62305. This is a very big standard. And again, static earthing is the dangers created due to static electricity, particularly in industries, explosive industries, chemical, petrochemical, oil and gas. In these industries, the static earthing is very important. There is a separate Indian and international standard for that. That is beyond our subject of discussion. Just to know that there are various types of earthing, I have included these two also, but we will focus mainly on system and equipment earthing. Now, what is system earthing? System earthing, always you should remember, system earthing is earthing associated with the current carrying conductor. The standard, I quoted from the standard, reproduced all these definitions from IS 3043, very clearly says earthing associated with current carrying conductor. That means system earthing should involve the current carrying part, a conductor, a part of the electrical system, current carrying system. It may be the neutral. Most of the times it is the neutral, either neutral of the source. That source could be a transformer, a source could be a generator. Here the objective, the system earthing objective is to protect the system. That means security of the system means it should ensure continuity of power supply to the healthy parts. It should isolate only the faulty portion. It should protect the equipment. It should protect the property. The objective for system earthing is for the security. Security means continuity of supply to healthy parts, limiting damage to the equipment, limiting damage to the network or system. This is the objective here. Whereas equipment earthing is earthing associated with the non-current carrying metal work. Let us say you have a switchboard or panel board in layman's language, a switchboard or panel board. Inside the bus bars are there, current carrying parts are there, bus bars, switch gear, all those parts are there. Outside metal enclosure is generally not current carrying, but it is capable of carrying current. It will not carry current in the normal condition. It will carry current only when there is a insulation failure inside, fault inside. But it is also a metal, it is capable of conducting current. So this earthing of this metal enclosure, metal enclosure, which is normally non-current carrying but can carry current, is called equipment earthing. Here the objective is safety of human life, animals and property. Even human can get electrocuted, animals can get electrocuted, and again there can be a fire also because of equipment current carrying through the equipment. Undue heating and fire accidents can happen. Accident, big property damage could happen. So here equipment earthing, the intention is safety of the human, safety of animals, and safety of property. Now coming to elaborating further on system earthing, There are 4 types of system earthing: solid earthing, resistance earthing, inductance earthing, and Peterson coil earthing. We are not discussing unearthed system here, but unearthed system is, again, it goes on to explaining a lot of things, but unearthed system we generally do not practice. So unearthed systems thing of the past. So almost today, almost at least in India, most of the systems are grounded, either solid earthing or impedance earthed systems. So we will discuss only these 4. But any query is there regarding unearthed system, please mail me, I will answer. Maybe we can think of a different session on discussing unearthed system and the damages of a very elaborate session we can have later in the year. So what is solid? There are 4 types of system. It could be solid earthing, it could be resistance earthing, it could be inductance earthing, it could be Peterson coil earthing. The last 3 are called impedance earthing. Generally, they are called impedance earthing also. Now, what do you mean by solid earthing? Solid earthing means, as the name itself suggests us, the neutral point of transformer or generator connected directly through an adequate ground connection. That means the connection is very solid. Solid in the sense there is no impedance, there is no resistance intentionally inserted in the neutral to ground path. Generally, you say in LV, we generally see this in Indian installations, the transformer neutral, generator neutral, using a copper or aluminum or steel bar, whatever it is, we connect it to the earth pit, earth electrode. We connect as directly as possible using a proper conductor of negligible resistance or negligible impedance. This is called solid earthing. Now, this is the typical diagram. You can see, this is the neutral, transformer generator neutral. There is no resistance here. It is connected through a solid conductor. Suppose there is an earth fault in the R phase. The earth fault current, major portion of fault current will flow through this. Of course, there will be a capacitive leakage capacitance will be there in the system between the Y phase and ground, and this is negligible. This is in milliampere or even less. So we will ignore this when there is a solid earthing. This current is significant. So whenever there is a fault, this current is significant, and as you know, the fault current is voltage divided by impedance in the system. So this is the phase voltage, R phase the earth voltage, R phase the earth voltage divided by impedance is negligible. Negligible means you can say in milliohms. So the fault current will be in kiloamperes generally. In solid earthing, whenever there is a single phase earth fault happens, the fault current will be in kiloamperes generally. So what are the advantages of solid earthing? Advantage is, because there is a huge current flowing, kiloampere current flowing, is easier. You can put a current transformer. The current transformer can be connected to a relay. So it is, fault is very easy. And the location, you particular each feeder you can provide a relay, and that relay will particular relay will trip, issue a trip command to the breaker, and you can localize the fault. Particular feeder has tripped means downstream of the feeder only there is an earth fault. So you can locate the fault, and once detection and location, isolation is a simple process. Healthier parts will not be affected, and transient over voltage is minimum. This transient over voltage is again the uh, phenomena of fault current to earth loop impedance. Here the earth loop impedance is negligible, since we are putting a solid connection. Earth loop impedance is negligible, so the transient over voltages are also kept to the minimum. The insulation, the stress on the insulation will be negligible, very less. On the neutral shift, the neutral is, because of the connection, the neutral of the source is always kept at the ground potential. So even during the fault, there is no even during a phase to ground fault, the neutral will still be in the ground potential because of the solid connection. So there is no ground voltage. There will not be any buildup of neutral to ground voltage. Yes, except some marking fault will be there. It will be there, but neutral shift will be very negligible. Of the equipment, ground insulation, enclosure insulation can be kept for a phase to ground voltage. Maybe in LT it is insignificant, because LT means the line to line is 450 volt, the line to earth is 230 or 240 volt. Here the insulation cost may not be very significant between a 240 volt insulation or a 450 volt insulation. But when you go to higher voltages, maybe 11 kV, 22 kV, and 33 kV, you can see 11 kV line voltage is 11 kV, line to line is 11 kV insulation. and the phase insulation is 6.35 kV. The insulation cost can come down considerably. So when you go for solid earthing, the insulation phase to earth insulation can be brought down. A very significant cost reduction can be achieved. Similarly, since the current is very high in kiloampere, generally, even some, so let us assume that nobody, people don't care for human life, let us say, but at least they will care for the equipment, because equipments are costly. They want to protect their equipment. They will definitely put a short circuit protective device like a fuse or a MCB or MCCB or breaker. They will put to protect their equipment. And these equipments, this short circuit protective devices are tuned to trip before the damage is done to the equipment. So when the current is in kiloampere, they will instantaneously isolate. So even in solidly grounded system, the fault is in kiloampere. So even the SCPD itself will, fuse itself will blow, breaker itself will trip. So there is, theoretically speaking, there is no need of any special earth fault relay or earth leakage relay or ELCB, theoretically. But again, due to various restrictions, the government is CEA regulations insist on providing a ELCB for making the protection very sensitive. But otherwise, if there is a single phase ground fault, because of the higher current, the SCPD properly attached device will immediately isolate the faulty portion. Lesser rated voltage of lightning arrestor and surge arrestor. When you want to select a lightning arrestor or surge arrestor for your system, the selection parameter rated voltage selection involves a term called ground fault factor or earth fault factor. Solid grounding is 0.8. The selection of rated voltage of surge rated highest voltage of the system into ground fault factor. Now for 11 kV system, if you say solidly 11 system voltage is 12 kV, if you put solidly earthed system, it is 0.8. So if you say 12 into 0.8, 9.6 kV is available, let us say the 9 kV surge, so you will go. But if you go for impedance earthed system, the ground fault factor may vary from 1.05 to even 1.732. So as you go unearthed or impedance earthed system, the expense on your surge arrestor will increase. Surge arrestor rated voltage, you have to select for a higher rated voltage. Similarly, there is a potential transformer standard 16227 part 3 or IEC 61869 part 3. In potential transformer specification also, there is a term called over voltage factor for PTs. There are various classifications given. For 1.2 continuous is throughout to cater to the system fluctuation. Then ground fault related over voltages. They say for solidly grounded system, if a PT is used in a solidly grounded system, the over voltage factor should be 1.5 for 30 seconds. That means because of the huge current flowing, the fault isolation will happen within 30 seconds. So it is enough if it carries a voltage factor of 1.5 for 30 seconds. If it is in resistance system where fault detection and isolation is possible, they say 1.9 for 30 seconds. That means almost twice system voltage you have to decide. Twice the voltage you have to decide. If it is unearthed system, the standard says 1.9 for 8 hours. So if the system is impedance earthed or unearthed, the cost and size of the PT will increase because you have to go for a higher insulation, higher over voltage insulation. But the advantage of solid earthing is if you go for solid earthing, the PT over voltage factor can be kept at the minimum most possible recommended by the standard. Similarly, cables, UE cables and E cables, you see 11 used a 6.35 kV cable can be used in 11 kV UE system. So put an earthed system, use a cable in an earthed system for 11 kV system, earthed 11 kV system, you can go for a 6.35 kV cable. The cable will be named as 6.35 kV UE or 11 kV E. So the same cable can be used, 6.35 kV cable can be used for a 11 kV earthed system also. The cost of cables also reduces. So my experience says the maximum cost in the industrial electric distribution is maximum expenses I have seen. Considerable expenses involved in cabling because so many lengths of cable at the plant. So a slight reduction in the voltage grading of the cable will lead to a huge total overall cost. So this is the advantage of solid earthing. But again, there are some disadvantages in solid. What are the disadvantages? High fault current means always you have to manage high accumulated heat will be there. Huge heating of the conductor will be there. If properly not sized or proper care is not taken to maintain, associated damages and disturbances will be there. The system has to be designed for the high fault current. The conductor sizing, if you want to provide a earth fault return conductor, the conductor sizing has to be for the maximum anticipated fault current. And because the system trips, there will be no service continuity, at least for the faulty portion of the period, depending upon your coordination. If your coordination is poor, maybe the incomer itself may trip. And more importantly, in rotating machines, if your installation has got rotating machines, there is sure chance of core damage in motors. If you have got because almost all industries are 70 to 75% industrial loads are motors. So if you have got a earth fault inside a motor, generally core is involved in the current path. The core cannot carry this much current, kiloampere current, and the damage will be done in milliseconds before the relay could sense and trip, or SCPD could trip. Damage will be done to the rotating machines. And similarly, since the current is more, even if you keep the resistance very minimum, because of the higher current, the GPR, ground potential rise will be more, and the touch potential hazard is higher. Because of these are the disadvantages of solid earthing. Now, what are the regulations say? What is the regulation says? Now, there is a regulation governing the electrical installations in India. If you see the CEA Safety Regulation 2010, rule number 41, sub rule 1, for medium, that is low voltage systems, that is voltage exceeding 125 volt but not exceeding 650 volt. They very clearly say the neutral conductor of a three-phase four-wire system shall be earthed by not less than two separate and distinct connection with a minimum of two different earth electrodes. That means it should be solid earthing. In the case of an alternate, then it elaborates in the next sub rule. In the case of an alternating current system, there shall not be inserted in the connection with earth an impedance. That means no impedance shall be inserted in connection with earth in low voltage systems. Low voltage systems must only be solidly earthed in India as per CEA regulation. Neutral point of every generator and transformer shall be earthed by connecting to the earthing system by not less than. This is again, there it says in the sub-rule it says neutral earthing of system. Here it says neutral point of the further elaborates generator or transformer. Why? Because here they say the low voltage system is generally, it is possible that the low voltage system is handled by non-electrical personnel like housewives, non-technical people in houses also can handle, or even in an industrial establishment, somebody, any non-electrical person can go for switching on, switching off some lights, or he can have access to low voltage installation, plug and socket boxes. He may put a drilling machine, grinding machine, welding machine like that. So since non-electrical people are having access to electricity, use of electricity in low voltage, so there should not be a need for any separate, strict implementation of earthing maintenance or even strict ELCB, and all. Maybe people may not want to invest. So they say, even if you don't invest in ELCB or ELR, you will definitely one owner may want to invest in protected devices for his equipment. So in solid earthing, even if such devices provided for protection of equipment, like a short circuit protected device or overcurrent protected device itself will operate, protecting the human beings. Even when you say, you remember the connection coming to your house, generally comes from a pole. They do not put any ELCB or ELR there. They put simply a fuse. They protect the electricity board people will put a fuse. Suppose in your house some leakage is there and you put access, because of solid earthing the current will be very huge, and the fuse will blow. They properly put fuse will blow. So that thereby, even without any need for going for a ELCB or ELR, in solid earthing, because of the huge current during fault, fuse itself will blow or breaker itself will trip. That is why the standard is insisting on solid earthing for all the low voltage networks. Below 650 volt networks, solid earthing is insisted in the regulation in India. When we come to then the next question arises, if solid earthing is so good, so perfect, so safe for people, why should I go for resistance earthing? Then Resistance earthing, as the name suggests us, the neutral of transformer generator are grounded through an impedance. The principal element of impedance is resistance. Now the problem is, we have to use this resistance earthing. We have to use this resistance earthing when the earth fault current, if not restricted through an impedance, will be quite large, like in solid earthing. It will damage the equipment, medium voltage, let us say generators or motors. Now, let me elaborate this. Now, any industry has got more number of 70 to 80% of industrial population is electrical equipment or motors, rotating electrical machines. Now, assume the motor's body is solidly connected to the nearest earth grid or earth electrode, whatever it is, connected to the nearest earth electrode or earth grid. Now, inside the winding is inside the core. Now, there is an insulation failure in the winding and an earth fault happens, and the earth fault current goes to the earth through the earth grid. Now, the core will be involved. The motor's core will be involved in the earth fault current path. From the winding to the core, through the core to the yoke of the machine, frame of the machine, then to the earth connection, then to the earth electrode, then to the natural earth, and back to the source through the conductor or through natural earth, depending upon the network. Now, since the core material is involved carrying the current during an earth fault inside a rotating electrical machine, the core material itself is of a high resistance material. It is not copper or aluminum, it is iron. And because it is made up of lamination, thickness is lesser, resistance is more. So by material characteristic, resistivity is more. By material construction, resistance is more. Huge heat will be produced in the core of the machine. When the earth fault happens, huge heat will be produced in the core, and the core insulations will melt and the core will become a single mold. Insulations separating the core laminations will melt in the heat, and they will start becoming a single large core, single volume of large core. Now the problem is, the very purpose of putting a lamination of the core is to reduce the eddy current loss and eddy current heating. Now the very purpose is lost. Now the core lamination insulation melts and it becomes a single bulk core, further compounding the problem, further increasing the heating. Now, if a winding failure is there, only a winding insulation fails in your motor, every reputed motor manufacturer has got a authorized local rewinder in any major town in the country. So you can take the motor winding insulation is damaged, the winding is damaged. You can very well get it rectified in the local rewinder, maybe authorized or well-known reputed rewinder, and you can get it immediately and put it back into operation. The shutdown time will be kept to the minimum possible. But imagine if a machine's core is damaged, the local rewinder or local person cannot and will not take core replacement. The particular segment of the core has to be removed and restacked. That will only be done in the motor manufacturer's works. So you have to remove the machine, send it back to the manufacturer's works, get the particular damaged core segment replaced. Probably this is the least priority job for the motor manufacturer, because in the stacking time is same. If the technician stacks a new core for cores for a new motor, his margins are more. So he will allot his free time only for service complaints. So maybe the time taken for core replacement is more. The machine comes back with the replaced core. Until that time, your plant will be down. If it is a critical motor, now your plant will be down. So how do I avoid this core damage? The core damage happens because the current is more. So I have to limit the current below the core damage limits. So that is possible by resistance earthing. Here you can see in the previous system we saw, there was a solid conductor between the neutral and the earth. Here I have inserted a resistance. So here the current is again ignore this capacitive current. I have shown, since it is there, I have shown, but this is negligible. The major portion of the current is fault current. If there is a R phase to ground fault, the current will take this path. Again, there are two kinds of resistance grounding. One is called high resistance grounding, where you are limiting the current to 15 ampere or less. What is the limitation? The limitation is the core damage current. If you ask for maybe for major large capacity motors or high voltage motors, if you ask the manufacturer, he will give you a core damage curve. The curve x-axis is in current, y-axis is in time. So he will give the damage level. beyond what current, what duration, his core will start damaging. So generally, for most of the rotating machines, electrical AC electrical rotating machines, motors, a typical value is 25 ampere per 1 second. Typical value. I'm just saying you can as well get the curve and study. 25 ampere per 1 second is the typical level for almost all motors. 25 ampere per 1 second. So if the current is more than 25 ampere per 1 second or lesser current for longer duration, it is I squared R again, I squared RT again. So if a lesser current for a longer duration or 25 ampere, more than 25 ampere for a lesser duration, the core is bound to melt and damage. So generally what they say, we want, if we want to avoid core damage to motors or generators for that matter, rotating machines, you reduce the current, set the earth fault current. Even in the worst case of a ground fault, the current has to be reduced below 25 ampere. Let us say you are setting to 15 ampere. So even in the case of an earth fault, even in the case of a single phase earth fault within a machine, rotating machine, the current will be restricted below 25 ampere. So there will not be core damage. So this is the guideline for going for the value of resistance. See the core damage curve of all the rotating machines set for the less than the worst level, worst machine, lowest permissible machines level. Less than that, you have to select the earth fault current. This is recommended machines up to 22 kV. Beyond 22 kV, there are not rotating machines. Even till recently, I was of the assumption that this is only rotating motors are available only up to 11 kV, because when I was up in the industry, this was the condition. But the other day, I was speaking to some persons. GE told me that they are having a motor, some 6,000, 8,000 megawatt motor, 6 megawatt, 8 megawatt motors are there in 22 kV. So nowadays, 22 kV motors are also there. So if you are having rotating machines in that particular voltage, you better go for high resistance grounding. Low resistance grounding. Now, low resistance grounding, as the name suggests, you reduce the resistance, you increase the current. Current is typical limiting values are 200 to 1000 ampere. Here, the advantage is, unlike solid grounding, the current is restricted to manageable level. It is not in kilo ampere anymore. But you can still detect it. You can put a 200 ampere CT or a 1000 ampere CT. You can put a current transformer in the neutral to ground path. You can put a relay and locate and detect, locate and isolate the fault. So this is low resistance grounding is practiced for transformers. Let us say you have a transformer, star, a delta star transformer, a star secondary star connected transformer. Generally, you solidly ground. Suppose you say if it is if the low voltage winding is if the secondary winding is a low voltage winding, you don't have any other go. You must go for solid earthing going by the regulation. Suppose let us say you have a 3.3 kV or 6.6 kV star winding, or you have 11 kV star winding. Now here you are not bound by regulation to go for solid earthing. Here you can want to avoid the damages to the winding. If you allow solid grounding here, more current will flow during a fault and it will thermally and electrodynamically stress the winding. Now suppose you don't want that to happen. You restrict the earth fault current to the full load current rating of the particular winding, secondary winding. Suppose the full load current is, let us say, 800 ampere. You put a resistance so that during a single phase ground fault, the current is limited to 800 amps. So even in worst condition of single phase earth fault, the fault current will not exceed the full load current rating of the winding. So the winding is not thermally or electrodynamically stressed. This is general practice for medium voltage secondary windings. Generally, people go for low resistance grounding. If the rotating, then the guideline is there. If the rotating machines are present in 3.3 kV, 6, because low voltage is ruled out, low voltage must be solid earthing only. If rotating machines are present in 3.3, 6.6, 11 and 22 kV level, the systems are grounded to resistor or reactor to limit the earth fault current. It need not be a resistor, it can be a reactor also. But the purpose is to reduce the current. How do you reduce is your choice. It could be by resistance, it could be by inductive impedance. If the rotating machines are not present at these voltages, then these systems can be solidly grounded. If you don't have any rotating electrical machine, then why put resistance earthing? Resistance earthing is again the voltage stress will be more. Neutral shift will be there. Voltage insulation has to be for the line insulation. So if you no rotating electrical machines are there, you go for solid earthing of these systems. Since rotating electrical machines are not present 33 kV and above, as at least as of now, there are no rotating machines beyond 33, beyond 22 kV. So generally 33 kV and above systems are solidly earthed, since you don't have the apprehension of core damage. EHV level, if you go to extra high voltage, that is 66 kV, 110, 132, 220, 400 and all, solid grounding is preferred because cost of insulation. As I said, the higher and higher, the difference of cost between base and line insulation is more. 66 kV and 66 kV by root 3 or 110, 110 by root 3. The cost difference in between the face to body insulation. If you go for impedance earthing, the insulation has to be designed for full line to line voltage. If you go for solid insulation, the face to ground insulation has to be designed for the phase voltage. It could be, the cost reduction could be very significant in EHV levels. So generally EHV people go for solid grounding to reduce the insulation cost. Again, whenever you go for EHV, definitely there will be unit protection schemes. Primary protection schemes will be there. Primary protection schemes, there will not be any intentional time delay. You cannot set a time multiplier is not there, a definite time is not there. As you must be aware, all unit protection schemes are instantaneous. So maybe the relay time is 50 milliseconds, the breaker time is 50 milliseconds. Within a 100 millisecond, fault will be cleared. So there is no need of apprehension of higher fault current flowing for a longer time. Because of unit protection, systems will react very quickly in EHV. So generally EHV people go for solid grounding. Then reactance grounding. Say why only everybody has to go for resistance? The resistance grounding, one big problem is heating.
Sorry to interrupt. Sorry to interrupt. Since like resistance grounding is so important and you have put down quite a lot of messages, I just want to hear from the audience whether the resistance grounding is clear or not. Audience, if the resistance grounding, like Sir has pointed out many important factors, I'm not really sure to what extent you have learned. If it is clear, can you just put again CC in chat? Yeah. Thank you so much. So Sir has talked about two important aspects. One is a solidly earthed systems. LV systems is solid for the reason behind the standards. When you go to the medium voltage, if you have a rotating machines, then means what to say, you have to go for a resistance grounded systems. If you don't have a rotating machines, then choice is yours. Like you can go with the solidly earthed systems. Why solidly grounded cannot be done EHV, or why solid ground can be done EHV? I guess like that slide what I am sharing is like answering the question. Means what, if you go for resistance grounded systems, the healthy phase voltage will jump, it will increase, and the insulation requirement is high, and that's the real reason why like high voltage or extra high voltage you cannot go for resistance grounded systems, you have to go for solidly grounded systems.
Resistance earthing, then why always resistance? What are the disadvantages of resistance earthing? Resistance and the disadvantage is made as heating. Whenever there is a resistance, whenever current flows through a resistance, yes, heat will be there. You have to manage the heat. So if the heat is unmanageable, you have to think of alternate ways of limiting the heat damage. The best part is the reactance, inductive impedance, where that is called reactance earthing or inductance earthing. The neutral point of transformer generator grounded through an impedance. Here the principal part is inductance. Here instead of putting a resistor, I am inserting a reactor. I am inserting a reactor in the neutral to ground path. You can go for reactance earthing also, but again, cost factor is also there. Inductors are costlier than resistance. So here, for system voltage is greater than 36 kV, it is preferable to use a reactor rather than a resistor because of the difficulties arising from heat emission in the event of fault in a resistance earthed system. Now assume the system fault current, ground fault current is phase to neutral voltage divided by the impedance you are going to put. Now higher and higher the system voltage, higher and higher will be the phase to neutral voltage. And for the same fault current, limiting fault current, let us say you want to limit the fault current, let us say 400 ampere. If 400 ampere equivalent ohmic impedance you are putting in the ground path, if it is a resistive impedance, then 400 ampere resistive impedance will cause more heat. Suppose for higher the voltage, and this 400 amperes or higher the voltage, for the same ohmic impedance, higher the voltage, higher current will flow and higher heating will be there. If you want to avoid the heating, you can go for reactance earthing, keeping the current level same. For 400 ampere, let us say, for you have to put, let us say, 100 ohm resistance. Instead of 100 ohm resistance, you put a 100 ohm inductance, inductive reactance 100 ohm. Same 400 ampere will flow, but that much heat will not be there. Now you have to manage the inductance only. But again the cost benefit analysis has to be done, because again inductors, because they are made up of copper or aluminum. Again the cost factor also has to be considered here. Then here also there are two types: low reactance grounding. Low reactance grounding, typically the current is limited between 300 to 1000 ampere, where you want to again detection is easy. 300 ampere to 1000 ampere, you put the appropriate CT and detect it. Again, various choices are given. Customer can do his own system, case to case basis. You can do his cost benefit analysis for going for each and every system. So current, but one thing is that current must be higher than the total capacity current of the per system. What is the capacity, total leakage capacitance or capacitance you have in your system? The reactive current, reactance, fault current, reactive fault current has to be more than the capacitive reactance in your system. The coil resistance is very less. We design the inductive coil to have a negligible resistance, so there is no apprehension of any abnormal heating. So people go for low reactance grounding, where they don't want heating, at the same time they want to limit the earth fault current. Then there is something called high reactance grounding. In high reactance grounding, the other name, it is known by very many names: Peterson coil grounding, or arc suppression coil grounding, or resonance grounding. Here the reactance value is very high, equivalent to the total system leakage capacitance. Every system, whether you like it or not, overhead system or ground system, suppose you have got a 11 kV overhead lines going. Now each conductor of overhead line is a capacitance, and the ground is another plate of a capacitor. The conductor is a plate of a capacitor, and the ground earth is a plate of another plate of a capacitor. There is a dielectric air separating them. So whether you like it or not, there is always every millimeter of the conductor there is a capacitance. For phase to ground capacity, interface capacitance also is there, but interface capacitance does not form part of earthing discussion, so we will ignore them. Every conductor, overhead conductor, has got a capacitance, leakage capacitance with the earth. Similarly, when you have a underground cable, armored cable, every conductor of the cable and the cable armor, conductor forms a plate of a capacitor, earth armor forms another plate. In between XLPE or PVC or paper or whatever insulation is there, the conductors separated by a dielectric is a capacitor. So every cable, every overhead line, every conductor has got a leakage capacitance to earth. These capacitances are huge. Capacitive reactances are actually very huge. So the reactances are huge. That is why the leakage currents we don't sense at all. They are in micro or nano amperes, let us say. So we don't even sense. Uh, Now, when you want to put a Peterson coil, in Peterson coil, whatever is the total system leakage capacitance, in your 11 kV system, leakage capacitance is so much. Let us say 100 ohm is there. You put a 100 ohm equivalent of inductance. It is called a Peterson coil. Here, during an earth fault, leakage capacitance, capacitive earth fault current due to leakage capacitance will flow. Then through the Peterson coil, another, because it is also equal ohmic value, equal current will flow, but in opposite direction. Because it is inductance, it will flow in opposite direction. They will cancel each other, like in your power factor correction system. One current is capacitive, one current is inductive. They will cancel each other. There will be no fault current. So this is the principle of Peterson coil grounding. This is again when the history evolution of earthing system. If you go, initially it was solid grounding. Then we want to move initially it was ungrounded system. From the ungrounded system, they want to move to solidly grounded system. They first equated system leakage capacitance with inductance. So evolution, if you see, then from ungrounded system, it moved on to Peterson coil grounded system. So Peterson coil grounding is very high reactance grounding. The current is negligible, and it is in the opposite direction to that of the system. Here, an inductor is connected between the neutral and the power system, the ground, having specially selected relatively high value of reactance, which is equal to the total system capacitive reactance. Now, when you come to the regulation, what does the regulation say about impedance grounding? Same CEA regulation, regulation number 48, sub-regulation 2, class 1 says, the neutral point of every generator transformer shall be earthed by connecting it to the earthing system, not less than 2 separate and distinct connection. Here, as when you discuss this, 48 is voltage systems having voltage above to 650 volt. Earlier, we have seen the system having CEA regulation for system having voltage below 650 volt, that is low voltage system. There, the regulation clearly said it must be solidly grounded. But here in systems having voltage above 650 volt, the regulation is giving a choice to the customer. The neutral point of a generator may be connected to the earthing system through an impedance to limit the earth fault current. Here, you can either go for solid grounding, or you can also have the option of going for impedance grounding as per the regulations also. Provided that the multi-emission system, neutral switching may be resorted. Suppose generally they say when 4 generators are kept in parallel, only neutral of one generator is kept on, other generators are isolated. This is called neutral switching. This may be adopted. Standard permits to earth the neutral of only one machine. If there is a harmonic current circulation, apprehension of harmonic current circulation, you can isolate the other neutrals, keeping only one machine neutral on. Similarly, in transformer, in the case of transformer also, the standards, the regulation says the generator or transformer neutral shall be earthed through a suitable impedance whenever you are the harmonic in the system is more, triplet harmonics is more. Whenever triplet harmonics is more and the triplet harmonics flows back to the neutral, because of this neutral current flow, whenever there is the interference in the communication circuit, when the current is flowing, it interferes with the neighboring communication circuit, you limit the earth fault current, harmonic current, by putting a impedance. This is also permitted as per the regulation, even for transformer. When the network is having lot of harmonic generating loads, you can also go for impedance earthing. So a general comparison of all the neutral earthing systems, various parameters are compared. Isolated means unearthed system, then graduating to Peterson coil, graduating to resistance, graduating to reactance, and then solid earthing. Transient over voltages, you can see poor. In Peterson coil, I said good and poor. Good in the sense, if the capacitance and reactance are perfectly matched always, 24 hours, 365 days, it is good. But due to switching on and switching off of system loads, if some capacitance or cables are taken out and the XL and XC does not match, then it is poor. Resistance also, it is depending upon the value of the resistance, it is good. Reactance again, depending upon the value. Solid earthing, very good, because there is negligible over voltages will be there. Limiting the 50 Hz over voltages, earth fault related over voltages, very poor in isolated and Peterson coil earthing. It is fairly good in resistance, reactance, and solid earthing. Fault current limitation, very good in isolated and Peterson coil earthing, good in impedance earthing, and very poor in solid earthing. Continuity of service, no tripping of the first fault. Isolated earthing and Peterson coil earthing, current is earth fault current is negligible. You cannot detect. So no isolation will be, no tripping will be there. So tripping is not there. Continuity of service is good. In the other systems, it is poor. Protection discrimination. That means if one system is not tripping, then the next upstream, next upstream, next upstream discrimination. In the first two systems, it is poor because current is not detectable. In the other system, depending upon the value of the inductance or resistance you are putting, or in solid grounding, it is good because of the current is detectable. You can go for better discrimination. Need for qualified personnel. Because in isolated earthing and Peterson coil, you have to perfectly match in Peterson coil, you have to perfectly match the inductance and capacitance. You need qualified personnel. So the system requirement is in that aspect, it is poor. Whereas resistance, reactance, solid grounding, the such called, even when the event of a fault, SCPD will trip or tripping will be affected. So there is no need for adjusting anything depending upon the switching on and switching off the cable. The reactances need not be matched. So there is no need of any qualified personnel. Even system will take care of itself properly. Coordinated system will take care of itself. Equipment earthing, as we said, it has nothing to do with the current carrying conductor. It is to do with the enclosures. There are two kinds of dangers when you come in contact with electricity. Shock hazard is classified as two hazards: direct contact and indirect contact. Direct contact is knowingly or unknowingly coming in contact with the energized part, live bus bar, live cable end, live terminal. Knowingly, most of the times it's unknowingly, ignorance. You think that supply is not there, supply will be there. Ignorance. Knowingly, nobody will do. Unknowingly, you have access to the direct live part. Indirect contact is you will not even know. Inside the earth fault will be there, the motor enclosure will be live. So you don't even know. If you touch the enclosure, you'll get a shock, like your iron box. iron box in your house, electric iron box in your house, geyser, pipe in your bathroom. So you don't even know whenever there is an earthquake happens, you go and touch it, you will get a electrocution. So there are two types of dangers: direct contact, and direct contact is coming in contact with the live part. Indirect contact is coming in contact with the not normally live, but it can become occasionally live due to fault inside. The shock hazard, the level of effect of current on human body generally, don't go by face value. I have taken some cautious approach. If the current through the human body is less than 1 milliampere, you will not even sense the fault. No sensation. Insensible current. If the current through the human body is more than 1 milliampere, less than 10 milliampere, let go current means no harm will be done. Let us say for a constant duration. If the duration is more or equally dangerous, let us say for a duration of 40 milliseconds, let us say. For the duration constant, 1 to 10 milliampere is let go current. Let go current means it will not do any harm. No adverse effect. 10 to 25 milliampere, muscular contraction will be there, painful. You will not be able to release your hand from the body, giving you shock. 25 to 50 milliampere, your heart pumping will stop. Ventricular fibrillation, this is dangerous, quite dangerous. That is why your ELCBs are rated for 30 milliampere. Human protection ELCBs are rated 30 milliampere because before the current starts affecting your heart, you want isolation. More than 50 milliampere, tissue burning happens. This is irreversible. It could be fatal, instant death. This is general. This is based on a study done by Charles DIgSILENT. You can search in the Google for DIgSILENT's experiment. Very elaborate study research papers are conducted. You can say the current, effect of DC current, effect of AC current, effect of current on men, effect of current on women, effect of current men weighing 50 kg, effect of current men weighing. The research is very extensive. If people who are interested, they can go and study the DIgSILENT experiment by Googling it. But this is a condensed table from DIgSILENT experiment. When they calculate the shock effects, generally they say human body dry resistance is 350 kilo ohm and the wet body resistance is about 1000 ohms. This is the logic. But whenever we design a system, we normally design for the worst condition. So we generally take 1000 ohms as the human body resistance for the calculations. Now, what happens when you don't earth your equipment? I have drawn a single phase circuit. System is solidly earthed. Low voltage system is solidly earthed. Let us say you have a MCB, a switch and fuse with the iron box or any single phase electrical load in your house. This is the equivalent circuit. You go and touch the enclosure. You just hold the iron box in your hand. Now, when there is equivalent circuit, if you draw, one is a load resistance, Ri is the insulation resistance, which is in mega ohms normally. RH is the human body resistance, Rn is the earth pit resistance or earthing grid resistance. Now, normal condition current to the human body is IL is equal to total system voltage divided by Ri plus RH plus Rn series resistance. Since Ri is in mega ohms, RH is in 1000 ohms, this is 1 ohm. These two are negligible. This current is mega ohms. Generally, the current through the human body during normal condition, when the insulation failure is not happened, is in microampere. That is 230 volt divided by, let us say, 1 mega ohm. That means 230 microampere, less than 1 milliampere, you cannot even sense it. That is why you don't even sense. Suppose the insulation fails, Ri becomes 0. That is phases touching the body. Ri is 0. Now the current through human body is only V by RH plus Rn. Now we will give some values. 240 volt, load resistance is 60 ohms. This is 1 mega ohm. This is 1000 ohm. This is 1 ohm. Before fault, 240 by 60, line current is only 4 ampere. This is mega ohm is microampere, insignificant. So 240 by 60 ohms is 4 ampere current is flowing. Normally for a 4 ampere load, you would have provided a 6 ampere MCB or a 6 ampere fuse. Now, when the fault happens, insulation fails, there are two paths. One path is the 4 ampere path. The other path is 240 divided by 1000 plus 1 ampere, 1 ohm. That is 240 by 1000, 1 ohm. Approximately 240 milliampere will flow. 240 milliampere current will flow through the human being. Now you imagine 240 milliampere is above 50 milliampere. Instant death will be there. Tissue burning will be there. The worst part is the line in the case of the equipment is not grounded. In the case of insulation failure, the line current has increased only by 240 milliampere. Before fault, it was 4 ampere. Now it is 4.2 ampere. The 6 ampere MCB or 6 ampere fuse will never blow, never trip. Here, the magnitude is also a concern. The duration is infinite. So, sure to affect the human being fatally. Sure to affect the person fatally. This is the bad effect of not doing equipment earthing. Now, that is why we are doing equipment earthing. Now, equipment earthing, how economically it can be done? Generally, connect the body of the enclosure to the local earth pit. You connect, there is a local earth pit for the transformer neutral, there is a local earth pit for your switchboard body. Now you draw the equivalent circuit. Same RI, same these two are coming parallel now. These two are coming in parallel. RE and RS has come in parallel, as you can see. Here, these two are in parallel. Now this is 1000 into 1 by 1000 plus 1. That is 1 ohm. 1000 into 1 by 1000 plus 1. Now 240, same logic, 240, 60, the line current is 4 ampere. Now the fault current is again, um, this is assuming that the equipment is kept at 1 ohm. This is 1000 into 1 by 1000 plus 1. Is approximately 240 by 2 ampere. This is 1 ohm. This is 1 ohm. 2 ohms in series. 240 by 2 ohms is 120 ampere. The line current will increase by 120 ampere. The current through this path will be 120 by 1000. Human body resistance is 1000 ohm. This is 120 volt drop will be there here. So 120 milliampere current will flow through the human body. So this 240 is divided into this 1 ohm and this combined resistance of 1 ohm. So 120 volt will drop here, 120 volt will drop here. This 120 volt divided by the human body resistance of 1000 ohm, worst condition, 120 milliampere will flow. Now here also, the current is fatal, more than 50 milliampere. But here the advantage is, since the line current has increased to 120 ampere, the fuse will definitely blow. 6 ampere fuse will definitely blow, or 6 ampere MCB will definitely trip instantaneously before any harm is done to the human being. So this is the importance of equipment earthing. When you do equipment earthing, even though the fault current is lethal, isolation is guaranteed. But there is a very big but, if and but here. This will be true only if the earth resistance is kept 1 ohm, or if the earth resistance is kept low. Here the assumption for this is R equipment earthing, RE is assumed this will be true. 120 ampere will flow only when the earth resistance is kept and maintained a low value always. But you know how well Indian industries are maintaining a earthing system. It is generally maintained only days before the electrical inspector arrives. So generally, the for this system to work, the maintenance of the low resistance earthing is very, very important. So this is also not practiced, because electrical person is not maintaining the earthing system. Even a non-electrical person touching the motor enclosure, coming in contact with the motor enclosure, can get electrocuted. So this is again not recommended in India, at least. So what you are doing, even if no one is maintaining the earthing system, still the system should work. What they say, equipment earthing with a protective earthing conductor. So they say you put a separate earth pit for the neutral, you put a separate earth pit for the equipment, you interconnect the two with a solid conductor like a GI earth flat or copper earth flat run around the plant. You connect all the earth pits to the earth grid. Now you are connecting a metal conductor between the two earth pits. Now we draw the equivalent circuit. Now you draw the equivalent circuit. Whenever the insulation fails here, whether you maintain this earth pit or not, current is going to flow through the solid conductor. Current is going to flow because you cannot change the parameter of this constant of the solid conductor. So this solid conductor, let us say the insulation is in milliohms, let us say 1 milliohm. Or now, whenever there is an insulation failure, forget you maintain the earth resistance here or earth resistance here. it becomes a phase neutral short circuit. The phase to earth fault will become a phase to neutral short circuit. So this resistance is normally in milliohm. So 240 volt by 1 milliohm is 240 kilo ampere will flow. So don't worry, even if you don't pour water, don't treat the earth bit, the resistance of the conductor will remain constant. So this fuse or MCB or breaker, whatever you have put here, will definitely instantaneously trip for 240 kilo ampere. So this is what is insisted in India by the standard. You have to go for this system is called TNS system. Time does not permit, otherwise we can discuss this in elaborately. This system, the previous system was called a TT system. This system was called a TT system. This system is called a TNS system. That is neutral is earthed solidly. Terra means natural earth, and there is a separate conductor for protective earthing, and does not depend upon the natural earth. So this is the system recommended for low voltage networks in India. In fact, it is mandated in the standard that it should be TNS only. So this is the significance of equipment earthing. Why should you go for equipment earthing? Why should you go for a PE conductor equipment earthing? Why should you go for a TNS system? Is even if someone forgets or ignores the maintenance of the earth bits or earth system, there will always be a safe isolation before the human gets endangered during a fault.
Now I am going to present you how to design an earthing system on software, how to use a software for designing earthing system, and what are the benefits of using a software. Okay, so let me share the screen with you. Yeah, can you see the presentation?
Yes. Yeah.
Okay, so this is about grounding it design using CEDAC software. So I don't know how much people have know about this CEDAC software. This is a software designed by Mr. PVsyst, which is he's from Canada. He has very good experience and expertise in earthing system designing, and he has very good contribution in making IEEE 80 standard. When you go to IEEE 80 standard, you can read his name at many places. Mr. Firdolabi, he has designed this software. Thus, this is well validated software for earthing designing and accepted internationally. So my agenda today is basically to introduce you about the software, and most important thing of this software is that solid resistivity, and how we do it, and what is the difference between doing solid resistivity analysis with the software and with thumb rules. So that I will show you. I will not tell you, I will show you everything. And difference between uniform and multi-layer solid resistivity. Basically, when you do with thumb rules, axle-based calculation, you go for uniform solid resistivity. But in software, we can go for multi-layer solid resistivity, and it is always advisable to go for it because there's a lot of difference between the two. The total grid design will change. And we can calculate earthing grid resistance, ground potential rise, GPR, safety factor concentration, safety factors we can check, we can calculate, and we can see them and how they are impacting the whole grid. That's the beauty of this software. Touch voltages and set voltages we will calculate. Actually, I don't have much slides. I will, after a few slides, I will take you to the software directly. Why do we need earthing software basically? There's a question. Because right now we are our earthing system designing is based on thumb rules, axle-based calculations, rough guidelines derived from empirical experiences, which varies greatly from person to person. So, and it is very time consuming, and definitely there is no concrete results. And you believe me, people have done calculations on Excel-based softwares, Excel-based worksheets, and when they have got the same designing done from me, and this saved at least 50% of the copper, 50% of the copper, because that is the difference between Excel-based calculations and the perfect software designing. So CDAX, what is CDAX? CDAX is basically the current distribution electromagnetic field grounding and soil structure analysis software. It is powerful and comprehensive set of integrated engineering software tools designed to accurately analyze soil structure. This is very important. Then earthing grade resistance and safety parameters of earthing grades. Now CEDAX has lots of modules, but for earthing grid designing, we use two modules basically. One is RESAP, CEDAX RESAP. This is the engineering software used to analyze multi-layer soil resistivity. And second is CEDAX MOLZ. These are advanced earthing design software. Rest of designing is done in MOLZ. So RESAP capabilities, basically, RESAP is used for multi-layer soil resistivity analysis based on actual measured soil resistivity data. So everything depends upon the data which is measured at site. So first of all, this data should be very accurate and should be very precise. Soil modeling, we do soil modeling. It's a crucial to grounding system, uniform soil model versus multi-layer soil model, that I will show you. How does it impact the overall grid design? Correctly interpreted soil structure, more accurate representation of soil model. This is the capabilities of RESAP. So this is the soil CEDAX screen. Basically, when we start, we see this screen. And there is the RESAP module. This is a MOLZ module. We are going to use both the modules to show you ground grid designing. So first, let us start with RESAP. RESAP, as I have already told you, it is used for multi-layered soil modeling of electrical resistivity. First, let me show you the sample data. Yeah. So for soil modeling, I have used this data. This is the actual data of soil resistance, which is measured at site. So I will use the actual data which I have got from my customer, one of my customers. This is, you can see, it's a measured soil resistance in ohms. These are the traverses, 1, 2, 3, up to 12 traverses. They have measured the data, and probe spacing is 0.2 to 150 meters. This is done as per Venner method. So average soil resistivity we have calculated here. This is the average soil resistance. Average soil resistance is calculated here, and all the parameters of soil resistance is converted into soil resistivity in this table. And as you can see, we have calculated average soil resistivity, which is around 1656 ohm meter. Okay. So this is very important. If you are doing some Excel-based calculations, you will use this value, 1656 ohm meter, as an average soil resistivity. But in our case, we will do calculations with software. So what we have done in software, we have input all the apparent resistance parameters from 0.2 to 150 meter depth spacing, and apparent resistance values we have put here. Now we will start analyzing this data. The computer will do it for us. These are iterations going on. Now we can see the result. Now you see that we were actually getting an average soil resistivity was 1656 ohm meter. But when we have interpreted this result with the RESAP software, then we have found 4 layers of the earthing, the electrical resistivity of soil. First layer is 63 ohm meter, and it is only depth of 0.12 meter, which is very less. It means it is negligible. Basically, it can be due to some error in testings. Second layer is 1669 ohm meter, which has depth of 24 meter. And third layer is 4000 ohm meter, which has depth of 50 meter thickness. And after that, you can see why I have chosen this data, because there is a tremendous change after this third layer. That is the soil resistivity here is 190 ohm meter, which you cannot guess, which you cannot make out from this data of average soil resistivity or the entire data. You can't make out that we have such a low resistance soil. Because now we'll put all this information in MOLZ software, and we will design a grid, and we'll see the impact, and we'll try to calculate the resistance of that grid and see the touch and step voltages. And we will also do the same calculations based on average soil resistivity, and we'll see the difference. First, let me tell you about something about MOLZ capabilities. MOLZ is basically multi-ground Z is a powerful and high precision software package dedicated to grounding analysis that can go well beyond the assumption of conductor equipotentiality. Taking into account the complex impedance of conductors, it provides accurate results for large grounding systems, even in extremely low or high resistivity soil conditions, and definitely in multi-layer soil conditions. So with MOLZ, we can calculate earthing grid impedance, GPR, ground potential rise, safe touch and step voltages, longitudinal and leakage currents, and the potential distribution in conductor network, which is sometimes very important. Potential and current density in soil or at the earth surface. Apart from this, the continued investigate transfer potentials. We can see the transfer potentials from one grid to another grid. Suppose there is a substation and some other grids are nearby, and we want to see the impact of, if in case there's a fault in one grid, what will the impact of on the other grid due to transport voltages. That also we can analyze and see. Interpret ground resistance measurements and high frequency impedance of grounding system, that also can be done up to 1 megahertz. We can inject currents and see its effect on the grounding system. Automatically generates safety tables of touch and step voltages. That I will show you how we do it in this software, determined according to national and international standards. Plots the grid hotspots. Basically, when we look for the touch and step voltages, it plots a graph and show in the hotspots basically. So it is very easier to see which portion, which part, and how much intensity is there of issues. So if we don't see any hotspots on the grid, it means everything is safe. And if it is not safe, it is going beyond the threshold limit, it will show in the terms of hotspots. So it is very easy to visualize and see and diagnose and analyze the system. You can very easily focus on dangerous zones, as I told, and identify our design decisions to optimize your final design. So now we'll go back to this my MOLZ software for demonstration. So this is an earthing grid which I have made. This is not the actual project. I have made it for demonstration only. This is around 200 meter. This 200 meter by 200 meter. And one more thing, we can compress this grid. Basically, you can see that my grid is, we can do this one. These are the equal squares. These are the all squares are equal. When you do calculation in Excel, you actually do this way. But in software, we can compress the ratio. We have compression ratio, and we can compress the grids along the edges, because we have more problem facing at the edges, touch and step voltages. So we can compress the grid with relation to your central portion. So that we can do. Second thing is, this is profile. This profile we have made at the entire grid area. So it is just to the software will calculate touch and step voltages of at the places where we have made the profile. Now, now we'll define this soil model in this CEDAX software. Now we have two options, like we can import the soil data from the file we have created, but here I'm having 4 layers of soil, but I'm not using these 4 layers. I'm using only 2 layers, that is 4000 ohm and 190 ohm. Why? Because yeah, I'm using only 2 layers, because if I use more layers, then iteration will take a lot of time. Sometimes it takes 3 hours to 8 hours also. So to reduce time, I have used 2 layer model only, because it is a demo only. Because I don't want that our total time goes in iteration only and we don't see anything. Now we have created a grid, and you can see the soil model here, labeling soil data. So it's the side view of the model, where we have put some conductors, ground rods, and these are the horizontal conductors. And you can see this is the first layer, 4000 ohm meter, first layer of soil, this is second layer of soil, 190 ohm meter. And we have inserted ground rods in such a way that we have deep penetration in the low resistivity soil of the ground rods, so that we can make use of that portion, low resistivity soil. Otherwise, our grid resistance will be very high. So we have defined soil model, we have defined conductors, and we have defined size of the conductors here. This is a radius in meters, and we can define the type of coating, default type of conductor, but MS or copper we can define here. We can energize that. I will do it afterwards. Like I have created a small conductor here, and if you see the characteristics, I have injected current here through this conductor in the grid to see the parameters to calculate ground resistance and touch and step voltage, GPR, etc. everything. And I have injected current 10,500 amps. So whether it is less or more doesn't matter, because it is just for a demonstration. So now we have defined the competition setting also. Okay, 50 hertz, it's good. Now I think I should run the software. So this iteration is going on, computer is calculating each and every conductor behavior, its resistance, its leakage current, total grid resistance, touch and step voltages as per our observation points. Each and every observation point, it is calculating touch and step voltages and ground condition rise. So iteration is complete. It didn't take much time, because I have reduced the system to 2 layers soil model, and everything I have done according to, so that it takes lesser time. So now here we can see the output results with output toolbox. So this is the examine portion of Molsy, examine tool of Molsy software. where we see all the parameters, effect of touch and step and resistance and values and everything is shown here. Basically, first part is report. First we see the report. This is a report generated by the software. So 10,500 amps current we have injected in the earthing grid. 50 hertz is our frequency, and total length of conductor is 12.9 kilometers. The soil data we have taken is two layers. First layer is 4,000 ohms. Second layer is 190 ohms. And the thickness of first layer is 50 meter, and second layer is definitely it takes infinite. The last layer it takes infinite. If there is no layer beyond this, after this, then it will take the last layer as infinite layer. So now you can see that it has calculated the ground impedance. Now ground impedance in our case it is coming around 0.7965 ohms. So this is very important. First of all, this is the most important part which everybody wants to see immediately. That will save for future. Okay. So this is the resistance we have got. And now we can see the other parameters. So before we go to the other parameters, I think we should first work on safety parameters because everything depends on the safety parameters. So this is the safety module of the software where we calculate the safe touch and step voltages. Because there are two things, the step and touch voltage we have achieved actually on the grounding system, and the calculation of safe touch and step voltages. Then we compare both and see whether our system, our grid is safe or not, because the touch and step voltages which we have generated on our grid should be less than the threshold limit, which we will calculate in this safety table. So as per standards, we are following the one IEEE standard basically here, and as per standards for conductor sizing we use 1 second, and for touch and step voltages for safety parameter calculation we take 0.5 seconds as a fault clearing time. Generally fault clearing time is very less. It should be less than 0.2 seconds or should be less than 0.1 second in best case condition, but we take it as 0.5 as a standard fault clearing time. And body weight we have taken 50 kg, we can take 70 kg also, but for 70 kg people can withstand higher touch and step voltages. So we will, as a worst case scenario, we will go for 50 kg only. And subsurface uniform soil resistivity is here 4,000 ohm, and frequency will take 50 hertz. IEEE standard 80 2013. As per this standard, all the calculations will be done by the software. Now, this is basically everybody I think must be knowing that on substations we provide a surface layer of gravel stone so that our withstand capacity of touch and step voltages increases. So how it is, I will show you that also. And this is a standard 15 centimeter surface layer thickness of gravel is provided on the substation, and soil resistivity is around 3000 ohm meter. If we calculate, I press the button and the software has calculated the safe touch voltage limit, that is 915 volt, and safe step voltage limit is 3198 volts. These all calculations are done by the software based on the parameters provided by us. So suppose if no surface layer of gravel is installed in the substation, then what will happen? Okay, it is increasing in our case because we have higher resistivity soil. There we have 4,000. Basically, what is happening? We have provided 3,000 ohm resistivity of surface gravel on the substation, and our soil resistivity is already 4,000 ohm meter, so it is very high. But if suppose we'll change it, suppose if we have 100 ohm soil resistivity, as generally you will find everywhere, then what will happen? If no surface layer is installed, then safe touch voltage limit will drop to 724 volt, and with surface layer installation, it will, sorry, yeah, with no surface do it again. Now, no, this surface layer, with surface layer, we are achieving safe touch voltage 724 volt, and when no surface layer is installed, it is come down to 178 is the safe touch voltage. So 178 volt is very less. It is very difficult to achieve sometimes this much less touch voltage in substations due to very high fault level current. And in case of fault, the most of the current will pass to the substation earthing system, earthing grid, to the remote source. And when very huge fault currents are passing to the earthing grid, then very high voltages are produced. So if there is no surface layer is provided, the safe touch voltage is 178 volt, and if it is provided, then our safety limit has increased to 724 volt. Okay, this was just for demonstration in case we are having very low soil resistivity of 100 ohms, but in our case we have very high soil resistivity here, which is around 4,000 ohms. So our safe touch voltage is 915 volt. So our all calculations will be based on these safe parameters calculated by the computer. So this kind of report is also generated where it is the fault in time 0.5 seconds, safe touch voltage, safe step voltage, surface layer resistivity, everything is mentioned here. Extra resistance of shoe, glove, etc. we are not taking into account because we want to see the worst case scenario. If we take that into account, then our limit will again increase, safe limit. We will okay it, go back to the examine module. Now you see these are competitions, scalar voltages, scalar potential. So you see this is the area of earthing grid of the substation, and now you can see a plot. Actually, you need not to go through the numbers to understand what is happening here. This is the beauty of the software. Now anybody can see and visualize what is happening and in which part things are happening basically. So yellow color represents less than 7,683 volt, and red color represents the maximum voltage of 8,423. This is not touch and step voltage. We are just looking at the voltage generated at the entire substations. Potential, total potential. This is not touch, this is not safe voltage. So this you can see it is lesser in the center. That is why we have taken the bigger square in the center and lesser in the at the edges. Now this was the scalar potential. Now we can sorry, the most important thing which everybody want to see the touch voltage, what is happening with the touch voltages. We will use safe limit, safety limit will use, we'll see whether our grid is safe or not. Yeah, here it comes. Now you can see here basically you can see maximum value which we have achieved in our grid is 743 volt. whereas minimum threshold limit is 915 volt. And you see there is no color in our, there's no, it's all white, so there's no problem anywhere in our earthing rate because our value is much lesser than the threshold limit. So this way it is very easy to see, visualize and understand the things. So suppose if we don't use any safety limit parameters, then what you see now, actually you are going to see the touch voltage pattern at the entire substation grid. So these are the touch voltage patterns, basically entire substation grid. This you have seen that there's no issue. Basically we go for this only because we only want to see that whether we have any issues in the substation or not. This shows that we don't have any issues and our substation is very much safe. But if you want to analyze it, how this, you can see a very uniform and very beautiful pattern because I have taken, let's say, uniform grids in x and y axis. So in center you see the voltage level is 743 and it is reducing towards this, it's blue 303 volt. At the edges it is around 597 and 523 volt. So this is the kind of pattern is emerging in that substation, but it is safe. That is more important. The same way we can see the step voltages. Generally, when touch voltage is safe, then step voltage will always be safe. There will not be any issue with step voltages. So we can see our step voltages, we are having maximum step voltage in the substation is 164 volt. And you know what is touch voltage, what is step voltage? Touch voltage is basically a voltage, when a voltage between the person standing on the earth surface and touching a conductor, any conductor which is carrying the fault current or the GPR at 1 meter distance. Maximum distance we take 1 meter, because as we take the lesser distance, the touch voltage will reduce. So beyond 1 meter one cannot touch, so we take 1 meter distance to calculate the touch voltages. Suppose this is a conductor and suppose this is 1 meter distance, so somebody is standing here and touching this conductor, there will be potential difference. You can see here there is a potential difference everywhere on the earthing grid. So if suppose somebody is standing here, there is a potential difference with this point and this point. If suppose this distance is 1 meter, then there is a potential difference below the feet of the person and the conductor GPR. So the difference between the person who is standing on the earth and the earth surface and the potential GPR of the conductor, that creates a touch voltage. And our effort is to make it safe anywhere in the substation. And what is step voltage? Step voltage is basically when anybody is standing anywhere in the substation and he has two legs, and between the two legs, which is 1 meter apart, is the two legs, what will be the potential difference? Because there is a potential difference, you can see the potential difference of all the substation, and when somebody is standing somewhere, then between its two legs there will be a potential difference, and if there will be a potential difference, the current will start flowing in the person between the two legs and it will pass through the heart, and when it passes through the heart fibrillation will happen and he may die. So we have calculated the maximum threshold limit, that is it should not should not increase more than 3198 volt as per the calculation, safety calculations, and we are achieving 160 volt. So our grid is safe, and that we can see, we can visualize it. That's the beauty of the software. And if you want to see, this is the step voltage pattern in the entire grid. So we have seen safety limits, we have seen touch voltage, step voltages, everything that which is very important. We can have different graphs also. 2D spot we have seen. This is for the touch voltage. Again, I am doing it. It takes some time. This is more complicated, not easy. Basically, this is more understandable. These graphs. Now, there's one more, few more things basically. That is the GPR of the conductor metal. GPR of the conductor metal, that is also very important, because touch voltage depends on two things. One is the GPR of the conductor metal, and other is the GPR of the ground, earth surface. Okay, so distribution of our surface ground voltages that you have seen here. That no, this is the potential at the ground. Now you will see the what is happening in conductor, GPR of conductor. So here we have injected the fault of 10,500 volt, and you see here the GPR is maximum, and after that current is reducing, distributing everywhere, and through this grid it is going to the remote source. And there's not much difference in this maximum and minimum values of the conductor, because we are using copper conductor of good size, and the area is we have taken is 200 meter by 200 meter. But sometimes if the area is very big and we are using MS conductor like we are doing in India, so in steel conductor, then you will find that the potential difference in the conductor itself is bigger than this, is higher than this, because of the voltage drop in the conductors, and that is well calculated by the software, which we cannot do with the Excel-based calculations.3D view is also there. We can see this is the horizontal ground plane, all conductors, and these are vertical ground routes distributing the current. So we can see each and every part of the grid and how it is behaving in different ways. Now basically, I will show you one more thing. Current density per unit area. This is very important. First I will show you, then explain you what is this. Okay. Now you see, this is a leakage current density in ampere per square meter. So maximum value here it is 433 amps per square meter, and minimum value is 1.17 ampere per square meter. So why it is less? So it is less in horizontal conductors and very high in the bottom of the ground rods. It is because We have to go back. No, no, no. Yeah, yeah. Okay. You see, you saw in the graph that leakage current density amperes per meter is less here and very high here because the earthing resistance is 190 is very low in this area and very high in this area. So current is tends to pass through the low resistance area to the remote source. But if we take average resistivity, average soil resistivity, then this kind of phenomena you will not see. We will take only one soil resistivity and we will do the wrong judgment, and the current density, the wrong current density will be calculated. So if we would have taken the average soil resistivity, that I will show you also that what will happen when we'll let me copy it so that we can compare both of them. Okay, now what is basically this is current density. By definition, okay, by definition, we can say that it is a one more safety aspect, checking the leakage current density of each of the conductor with allowable current density. Actually, it is mentioned in the IS. Basically, there is a calculation formula given in the IS table to check the current densities of the conductor, and this is the formula. The 7.57 is the constant into 1000 divided by under root rho into time. I have taken two layer soil model. First layer is 4000 ohms, second layer is 190 ohms. So rho here is 2, and the third one is a uniform model, which I'm going to show you later on. So if we calculate the current density as per the IS, then it is coming around 169 ampere per square meter in the area where we have high resistivity of soil, and 775 ohm meter in the area where we have low resistivity of soil. This you cannot calculate or analyze and foresee if you're doing Excel-based calculations. And what we have achieved is 42 and what we have achieved is, this is the red portion for 33 maximum, the yellow portion is maximum 43. For 33 and 43, which is less than the required. So we can say that our earthing grid is very much safe, and what we have designed is accurate, and we don't need more earthing conductors or ground rods, because there is a valid question every time people ask that how many ground rods should be there, how many conductors should be there. Basically, we are having lots of conductor here. This is to counter, this is to bring touch and step voltages into control. These are the conductors. Basically, they are not doing much, contributing into this lowering the grid resistance. Because if I remove lots of conductor from here, even then I will get almost the same grid resistance. But we have to put so many conductors to control the touch and step voltages, because there are voltages everywhere, and we have to control the differential between the 1 meter distance as per the safety norms. So what we do that we first design the grid, then do the iteration and check for the hotspots, and everything is clear. Then we reduce some number of grounding conductors, and then again check basically what we do, we optimize the earthing grids so that we use minimum or required number of conductors. We don't over design the earthing grid, because most of the times what happens that, as I told you earlier, that one of my client, he has it was a project in, I think, Abu Dhabi, or yeah, somewhere. It was my first project, 500 kilovolt substation. So it was there, and they have designed that grid with the thumb rules in Excel software. Then they approached me. They were confused. It was a bit complicated. Soil distribution was very high. So I did the designing, and when I calculated, I did like various iterations I have done and made the use a minimum number of conductors to make grid safe. And then they have told me that almost 50% of copper, 50%, that grid was almost more than, I think, half a kilometer big. So huge amount of conductor they have saved. And apart from that, they were 100% satisfied that what they are doing is 100% correct. So current density basically should be in limit. Current density, if current density increases, then the beyond the limit, what happens that temperature of the conductor will rise. Temperature of the conductor will rise tremendously, and it will increase the temperature of the surrounding soil. When the temperature of the surrounding soil will increase, what happens that its moisture will evaporate, and the soil resistivity which we have calculated, soil resistivity, it will change. It will start increasing. As the soil resistivity will start increasing, the current distribution will start change again, and it will form a loop basically, and it will keep on increasing and increasing and increasing soil resistivity, and it become more and more insulator. The soil becomes more and more insulator because there will be no moisture after a few microseconds or seconds. There will be no moisture in the soil, and our grid will fail. So we should design grid in such a way that these things are remain under control. Okay, more things I'll show you. There's so many things basically. But PDS we can see top view or 3D view. Oh no, this is not what I want. We'll use color because I don't want any text here. It is difficult to read text. It's easier to visualize. So basically, it shows that two size of conductors we have used. It shows them those. If we have used more size of conductors, then it would have shown all with different color coding. Now let me see if I say something else which is of your use. These are the profiles we have made to calculate step and touch voltage, and this is the current injected here. That software can has shown that we have injected current here to calculate all the parameters. So I will save one more graph from here. These are touch voltage block that I will save, so that when we'll do with average soil resistivity, we can see the difference. Okay, now I'm going back. I'm closing it, and we will do the entire exercise again with the uniform soil resistivity. Soil model will change. As we have seen here, it is average soil resistivity is 1656. We will make it uniform 1656 ohms. 1656 ohms meter. Now we have taken uniform soil resistivity in place of horizontal layers. You see, now there is only one layer everywhere. Earlier there were two layers. Now grid is same, current injected is same, ground rods are same. We'll run the software. So I just wanted to show you that how much misinterpret we can do if we don't do proper soil analysis even. So two things are very important. One is the proper soil analysis, and second is the split factor, like current division factor. That should be very correct. If we are using high current, then it may give us wrong results, and we may make extra safe grid. We may design extra safe grid. Now we have done nothing. We have only changed from uniform multi-layer soil to uniform soil, and we see the report. What happens? Now you see the report. It has the impedance of the ground has become 3.04 ohms. So now you see the difference. With multi-layer soil model, it was 0.79 ohms, and with uniform soil model, with uniform calculation, thumb rule kind of a thing, with the same grid, we are having 3 ohm resistance. We are achieving 3 ohm grid resistance. Now you see the difference. It's more than 3 times. Now, if we want to make this grid safe, then we have to put more conductors, more ground rods, and it will be very expensive, more than 3 to 4 times, 5 times expensive than it should be. So now we can realize that how important is the proper soil modeling. Now we'll see the other parameters. We'll look for the touch voltage. Is the most important factor which we see. Safety parameters will little bit change because this surface layer uniform, the soil resistivity layer has changed from 4000 to 1656 ohms. So our now safe touch voltage is 819 volt. So attention takes some time. Now you see our grid is not safe. The grid which was safe earlier, now it is not safe. You can see the spots here. Wherever you see the spots at all the edges in the center, it means that area is not safe for touch voltages, and the values there are more than the threshold limit of 819 volt. These areas are safe, but these areas are not safe. We have not done anything. We have just taken the soil resistivity as a thumb rule, and our grid shows the problem. Look, this is the difference. This is a safe grid, standard at 43, and this is the unsafe grid. And if you look at the current, okay, the most important factor now, again, second one.
Yeah.
I have done actually, I have done because there's so many things I keep on showing them, but I want to
True,
one
like
more.
that.
Let me show the current density, how it is behaving now. So now this is the current density chart, which you can see it is 119 to 15. Earlier we were having the same current density in this region, but now it is changed. So current density, grid resistance, current density, these are the two very important factors to decide how much conductor we should, and the touch voltage definitely, how much conductor we should use in the earthing system. Yeah, so this is the difference in the. Yes, I am done actually. I have shown everything. I have shown the difference in the, because this is what I wanted to show, that if we do something on thumb rule based, even though we have done only thumb rule based calculation with soil resistivity, and if we do the thumb rule calculations with grid also, then things will change more. It will become more vast.
So I mean, what to say? Let's looking at this scenario. Means if you go with an Excel sheets, you can do the still calculations based on IEEE 80 for an air insulated substations. No doubt about that. But the limitation is you cannot do the multi-layer soil. You can go with only a single layer. And like touch voltage is increasing at means one place. Still, you can put this conductors uniformly only. So that means that's an unnecessary over design. You are putting quite a lot of coppers inside the ground, which is going to not help you anything. And means what to say, that's a waste of money which you are putting inside the ground. But if you go to the CDGS simulation software, like means before going to CDGS, let's look at maybe some other simulation softwares which are available in the market, maybe like ETAP or SimGrid. So means what to say, there you can probably go with again same IEEE 80, and there are a few stuffs, but it is not as great as CDGS from means what to say many aspects. That's what like maybe Deepak has straight away jumped in. I guess like most of you may not know about the simulation softwares, and even I have received some comments like whether the software is free. No, the software is not free. Okay, so if you go with the ETAP, again means what to say that accuracy is limited. Say example, one point Deepak was what he is trying to say is like finding out the split factor. You have to assume the split factor if you are going with ETAP or SimGrid. Like you may typically take 0.7 as a split factor, but that again based on IEEE 80 some tables which you will not be able to exactly work out what's the split factor. If you want to work out only the split factor, there is a dedicated model in CDGS, so that you go and find out the more realistic split factor, so that you can optimize the earthing design. You can go for a multi-layer soil resistivity, like 4 layers, which is there, like for the time being, like because of the time constraint, Deepak has stringed it to the 2 layer. You can go with a multi-layer, and you can optimize the earthing. On the other side, means what say, you can put means what say non-uniform conductors, like you can put conductors wherever you want, or where there is a touch potential rise or a step potential rise, you can probably means only focus on that particular area and you can reduce it. And the software is going to, of course, the software is costly and study is like means a bit expensive, but for sure that's going to save lakhs rupees or dollars, maybe thousands of $1,000 if you have done your earthing system carefully. That ensures the safety at the same time, that is also ensuring means what's the economical. And somebody has asked the question like transient GPR, transient ground potential rise. So means what say where this other simulation softwares like ETAP or SimGrid couldn't reach the CDGS is like GAA substations, gas insulated substations. For a gas insulated substations like TGPR you need to calculate, and like means when it comes to the gas insulated substations, I guess like means what say CDGS is the only software few years back, but now there are few other new softwares which are coming in, but means what say this is a well proven simulation software for gas insulated substations. And that's probably pretty much introduction about the CDGS simulation software. I guess like Deepak has presumed that audience know about all this background for the audience, and he has directly jumped into the simulation software. And like he has explained, like CDGS software itself has quite a lot of models, high freq mods, like I mean, I'm not really jumping into all those things. Means what is it? Like free trial will be available, which you may not be able to simulate, which you can, I mean, so say get the software. You may not be able to simulate, but you can see the equipments and everything. Maybe someone from our team, can we just put like means where you can download demo or something? That probably means somebody has asked. So like that might be helpful for the people, those who want to just explore the simulation software. And they have in their website itself, they have compared. Like there are quite a lot of beautiful articles with the case studies. Means what's say where do we need to go for the simulation software and what's the optimization which we can do. So that's there in the means website of means what's say CDGS itself, which you can check.